All right, in this new section, which is going to be a little easier than the previous chapter we did, there's more concepts, and I think it's more straightforward, so that's why I'm saying so. The first thing we wanted to define in chemistry is what is energy. Energy is something that's present within an object, and the energy causes items to move or to stop, or energy is something that will do work. That's how it's defined. Now, the reason we use the law of, just like for biologists, the law of evolution is very relevant because it is the basis of a lot of biological processes and the relationship between organisms. And for example, the law of gravity for physicists is also very important because it explains the fundamentals of physics. The law of conservation of energy is as essential for a chemist. The law of conservation of energy, let me write it down first, states that energy can neither be created nor destroyed. It always changes its shape. So the law is stating that energy cannot be created nor destroyed. So in other words, I cannot take a magic wand and disappear any sort of energy, or I cannot take a magic wand to increase energy in a system. Now, this sort of makes sense because, for example, if you're ironing your clothes or fabric, then electrical energy is converted to mechanical energy, and that can be converted to heat, and it can release heat. So pretty much energy keeps on moving. For example, solar energy that is present in the sun is captured by the plants through a process of photosynthesis into chemical energy, and this chemical energy is then converted to potential energy and kinetic and so forth. So we'll talk about different kinds of energy in this chapter. The first definition of work is that work is something you do in which you require energy. So whether you're riding a bicycle, or even if you're static and your heart's breathing, or it's pumping blood, or water goes over a dam, these are all examples of what we define as work. Now, there is a form of energy that is associated with just storage, and that energy is called as the potential energy. So potential energy is the energy that is always going to be stored within a system. So for example, over here, when you're filling up gasoline in a car, then the gasoline molecules store energy in chemical bonds, and these are called as, this energy is called as potential energy. We will pretty much talk about potential and kinetic. The rest of the energy, for example, solar, nuclear, mechanical, electrical, radiant, there are so many different kinds of other energy which we will not mention, but we will talk about these two major kinds. So for example, if you have a height, and I'm trying to draw a mountain. I'm not a very good artist, as you can tell. If there's a rock present over here, and there's a rock present over here, so there's a rock at the base of the mountain and the rock on the top. The rock on the top is going to have more potential energy because it is at a higher position. So potential energy has a lot of times has to do with the position of the object. It's just a resting state. So for example, if you take a small little tennis ball and you throw it up, or a basketball, then as far it goes up, it will stop at the top for a fraction of a second and come down. So that fraction of a second that it did, that energy at that state is called as potential energy. However, when that ball starts falling down, that energy is converted into kinetic energy. So kinetic energy has to do with motion of a substance or of matter. And so, for example, swimming or water flowing, or if you're doing a good workout, or now the gasoline burning in the car to power the car to move, are all examples of kinetic energy. Both potential and kinetic energy, when are converted to one form or the other, usually sometimes energy is released as heat in major systems. The heat that is released is measured in units, their calories or joules. And I just want to talk about the calories, because the nutritional calorie that you hear about on certain food items or labels are based on this concept. So the amount of heat that is generated from a substance can be measured through an instrument called as calorimeter. A calorimeter is basically a simple, shown over here, the styrofoam cup in which you have water here and you have got a stirring wire here and a thermometer stuck in, and you sample metal. So any reaction that takes place within this medium will either increase or decrease the thermometer reading, and the heat lost or gained is then reflected through a calorimeter as to how many joules of calories have been generated. So when nutritional calories are measured, they actually burn the food in a little instrument, which is a calorimeter, and the temperature, the heat that is generated by the burning of that meal generates heat, and that is measured through the thermometer to express as to how many kilocalories that is. So for our purpose, we want to look at some nutritional calories for the 3 macromolecules that are present within our food: carbohydrates and proteins. Both, notice, generate 4 kilocalories per gram. So if you have a gram of carbohydrate, it's going to burn off 4 kilocalories. On the other hand, if you notice, lipid has twice as much. It generates 9 kilocalories per gram. So that's why it is called as the stored form of energy, because when people who go into Atkins diet, for example, they stop taking carbohydrates, so they're forcing their lipids to burn off. So these are just examples of how this is written on food label. Now, on food label, energy is shown with a capital C, and that is 1 C is equal to 1,000 kilocalories. So we will use, in scientific experiments, you usually use the term kilocalories. So let's go on to the next slide. Here is a slide in which we see a table that represents the different components of certain food items, the carbohydrate, fat, and protein that is present in each. Now notice banana has 26 grams of carbohydrate. So using the dimensional analysis, if I was to express how many kilocalories is generated, then I know that 1 gram of carbohydrate is generating 4 kilocalories of, let's get the spelling correct over here. It's generating 4 kilocalories. So that means this is going to be 104 grams. Plus, notice that there is 1 more gram of protein and gram that will give you another 4 grams. So the total is about 108 grams, and this is actually just using significant digits. It's been rounded off to 110 kilocalories that is generated through 1 banana. So this is important for those of you who are going into allied health careers, because you can see different composition of different food, and thus develop a nutritional plan for different people. Now, the amount of meal that we take is going to generate a certain amount of energy, and if you want to burn that energy off, the next table that is shown over here shows us that how much time can be devoted to a certain activity to burn off. For example, sleeping will burn off 250 kilojoules, or let's just go into the kilocalories. That's the one we want to use. I'm going to cross these out. Looking at the table on the right, which indicates that 1 hour of sleeping will burn off 60 kilocalories, and you can see 1 hour of running would do 750 kilocalories. So again, using dimensional analysis,